Okay, so this is my fourth time attempting to make this video. Hitting some technical difficulties, but hopefully we got it this time. So I've already worked through most of this stuff. I'm just going to explain what I've done up until this point. So the last video we left off talking about how we were going to evaluate an integral that is used in probability and statistics for the standard normal distribution. And before we can get to that, I want to talk about some notation here. The notation that I'm using here, this is R2. So I'm looking at a double integral of the function f of xy dA over R2. What I'm doing is I'm integrating over the entire xy plane. So instead of just looking at a region like a rectangle or a circle or some type 1 or type 2 region, it's all of R2, the entire xy plane. That as an iterated integral in rectangular coordinates can look like this. So my interval on my x and my y are both going from negative infinity to infinity, where these are looking like improper integrals from calculus 2. What we need, though, is a description for this same iterated integral, but in polar coordinates. Now this should actually be f of r theta dA. And we're not even going to use it in that form anyways, but I want to talk about how we can move this idea into polar coordinates. So I defined this set down here that I'm calling dA. D stands for disk. A is going to be what the radius of that disk looks like. The disk looks like this. It's centered at the origin. The radius is A. And as a set, it can be described this way. R goes from 0 to A. Theta goes from 0 to 2 pi. R2 can be thought of as this disk if I let A go to infinity. So d sub A is technically not a function. This limit notation, we'd have to be careful with how we're using this, but you can kind of intuitively picture that as this disk gets bigger and bigger and bigger, it starts to envelop all of R2. So in the limiting case, we just say that this disk goes to R2. I'm going to use that idea in this problem that we're going to do. So here is the example that I wanted to show you. We want to evaluate the integral from negative infinity to infinity of e to the negative x squared over 2 and show that it comes out to the square root of 2 pi. The way we're going to do this is we're actually going to start with a slightly simpler integral, the integral from negative infinity to infinity of just e to the negative x squared, or not over anything. And I'm going to set that equal to I, to give it a name. Now, instead of trying to deal with I directly, which we know we can't really do, we're going to try this clever trick. I'm going to look at I squared. So I squared would be I times I, this integral times itself. One thing I know about integrals is if I change the label that I use for my variable, it's not actually changing the value of that integral. I can call this x, I can call it q, I can call it giraffe if I want. I don't know why I would do that, but I could. So the value of that integral would be the same thing as long as I changed all the variables into the new variable. My point there is that if I was going to write I squared, I could write this integral times itself, but in the second integral, I could change the label that I'm using, and it doesn't actually make any real difference as far as what this comes out to. So I'm going to change the x's into y's in this second integral. Now the reason I'm doing that is because this can be turned into an iterated integral here. If I were to recognize that this is a function of x, this is a function of y, it's like that property we've been using to split up iterated integrals where the integrand looks like a product of a function of x with a function of y. But doing that backwards, pushing them back together into a single double integral, I would get this as my new integrand. That x squared plus y squared there is giving me the perfect example of where polar coordinates would be really helpful. So moving that up a little bit, I can change this into polar coordinates by letting x squared plus y squared become r squared. And then because we're making the change into polar coordinates, my dA no longer looks like this, dx dy. It's going to look like r dr d theta. And then I have to also change what this double integral looks like. Remember, we're integrating over this disk now, dA, where a goes to infinity, because that describes the same region as this. They both describe all of R2. Okay. Now, after doing this, because this R makes an appearance, I'm suddenly able to use a U substitution to evaluate this. So we're going to start by creating an iterated integral. Remember how we described that set dA? The variable theta goes from 0 to 2 pi. The variable r goes from 0 to a. And the integrand, looks like a product of a function of r times d theta. So the d theta can be brought out here. I can deal with that as a separate integral. When I want to integrate the function that's given in terms of r, my u substitution, the natural one I would want to use is u equals negative r squared. So I did that here. That u substitution leads to this integral. Okay. Now, you'll notice that I have a negative here. I can use the negative to flip the order of my limits of integration. That would make it a positive 1/2 once I've done that. So that's why you're seeing the negative a squared down here in the next step. I switched the order, got rid of the negative. Evaluating this integral, the 1/2 and the 2 are going to cancel out from here. E to the u, I'm going from negative a squared to 0. So that becomes e to the 0, which is 1, minus e to the negative a squared. And that whole thing is times pi. That was from this part right here. If I take a to infinity, this exponent is going to go towards negative infinity, which e to, that's going to take this term all the way down to 0. So that becomes pi times 1, which is pi. Okay, now that's what I squared is equal to. I squared up here. So that would mean, if I took square roots, that I has to equal the square root of pi. Okay? Not plus or minus. The reason I know it's not plus or minus when I take square roots of both sides is because, again, I was originally defined to be this integral, but this integrand is positive for all values of x, which means the integral itself has to come out to a positive number. So there's no way that it could be a negative root pi. Okay, so we have this. Now we're going to try and return to the original integral that we wanted to deal with, e to the negative x squared over 2. So I'll write in what we just found. Actually, we already have it down there. So let's look now at e to the negative infinity, or sorry, I don't know why I call that e, the integral from negative infinity to infinity of e to the negative x squared over 2 dx. I'm going to make a u substitution here. Okay, I'm going to set u equal to, let's see, what did I do before? I'm going to set u equal to x over root 2, which would make du equal to dx over root 2. If I isolate the x in each one of these, I get root 2u equals x, and root 2 du equals dx. Okay, now think about what that does to this integral. So if I plug a root 2u in for this x here, when I square it, it becomes negative 2u squared over 2. The 2's cancel. So I just end up with e to the negative u squared. My dx becomes root 2 du, but I can pull the root 2 out so that I have du here. And then because I did a u substitution, I have to make sure and change my limits of integration. But if x is going to infinity in this expression, then u would also pretty clearly be going to infinity. Same thing here. If x is going to negative infinity in this expression here, then u is also definitely going to be going to negative infinity. So the limits of integration don't change really. This integral we just figured out was equal to the square root of pi. Change of label, I have u's instead of x's, but that doesn't, like we said, that doesn't make any real impact in how we evaluate it. So this becomes the square root of 2 times what we now know is the square root of pi. Putting those together, this comes out to the square root of 2 pi. Okay, so interesting technique for evaluating that integral. Like I said before, there's no way to evaluate that integral using antiderivatives. It's actually been proven that there are no elementary antiderivatives for that function, but this is like your workaround. I can't think of any other cases where this technique works for a function like this. There may be some out there, so I'm not implying that this is a technique that gets used all the time, but it's a kind of a clever way of handling a problem like this. If you're interested in knowing more about this integral, the one that we evaluated originally, e to the negative x squared from negative infinity to infinity, this is called the Gaussian integral. It's worth looking up if you're interested, but that's pretty much the only time we're going to see it in this class. And that's it for 15.3.